Welcome to our comprehensive video tutorial on the Cox, Ingersoll, Ross model, often abbreviated as the CIR model. This model is widely used in the finance world, especially for modeling interest rates. The CIR model is a mathematical model used to describe the evolution of interest rates over time. Developed by John Cox, Jonathan Ingersoll, and Stephen Ross in 1985. It offers an improvement over earlier models by incorporating mean reversion and stochastic volatility. At its core, the CIR model models interest rates are using the following stochastic differential equation. dr underscore d equals k theta r underscore d dt plus sigma square root r underscore d. To break this down, we have three key parameters: k kappa, theta theta, and sigma sigma. Kappa, k, represents the speed of mean reversion, theta, theta, is the long-term mean level, and sigma, sigma, is the volatility. The term dw represents a Wiener process or Brownian motion. Let's explore each parameter in detail. Kappa, the speed of mean reversion, dictates how quickly the interest rate reverts to the mean level theta after deviating from it. If kappa is high, the interest rate quickly moves back to the mean level. Conversely, a low kappa means the interest rate stays away from the mean level for longer periods. Theta represents the long-term mean level, or the average rate toward which the interest rate tends to gravitate over time. Think of it as the equilibrium point of interest rates. For instance, if theta is set at 5%, the model suggests that, over time, the interest rates will average around 5%. Changes in theta shift the entire path of the projected interest rates up or down. Sigma represents volatility, which affects the randomness or variability of interest rate movements. Higher sigma values result in more volatility and more significant random fluctuations. This is crucial in scenarios where market uncertainty is high. Let's look at an example where we vary sigma while keeping kappa and theta constant. Now, let's see how the CIR model differs from other interest rate models like the Wassercheck model. One primary difference is the non-zero lower bound in the CIR model, meaning it prevents interest rates from becoming negative. In contrast, the Wassercheck model may allow for negative interest rates due to its simpler linear relationship. The CIR model's square root term in volatility ensures a strictly positive rate. A practical application of the CIR model can be found in the valuation of bonds and interest rate derivatives. For example, the pricing of zero-coupon bonds heavily relies on accurate interest rate modeling. Here's a question: how would increasing sigma affect the bond pricing using the CIR model? Think about the increased randomness and higher fluctuation in the interest rates. Answer: increasing sigma would lead to greater uncertainty in interest rate movements, generally increasing the risk premium. This would likely decrease the bond price because the expected future payoff needs to compensate for higher risk. It's crucial to understand these dynamics, especially for financial professionals involved in risk management, portfolio optimization, and derivative pricing. With this, we have covered the fundamental aspects of the Cox, Ingersoll, Ross model. We've explored its equation, parameters, comparisons with other models, and applications. We hope this detailed explanation helps you better understand how the CIR model functions and its significance in financial modeling.